What's up? What's up? It's your man Jimmy Chan. So today we're talking about set theory. So I want you to kind of, go through all these terminologies that you're going to see, and I want you guys to understand what they are. So all a set is just a collection of the elements that you're either given or you can make up. So let's say I make up a set of elements, right? So now the most important part is that we always represent those sets with capital letters. So let's say I use A is equal to the set of 1, 2, 3, dot, 10. Okay? So there I have 1 through 10, increasing by 1. All right. Now, notice that I always put a set in these so-called squiggly brackets. All right. So in the English language, this is just saying the set of. Okay. 1 through 10. All right. So this right here, the way I listed those elements, we would call this the roster method. Now, I could also write this in the so-called set builder notation, but before I even say that, notice that the definition of roster method says list of member or elements of a set. Now, set builder notation says a description of the conditions that must be met in order for an element in order for it to be an element of the set. Okay, so if I was to rewrite this, I want to write it as A is equal to a set of X such that X is an element of the natural number, and I'll show you what a natural number is and what that funny looking E is, and X is less than or equal to 10. Okay, so if you think about it, now I'll explain what a natural number is, but this will be the representation in set builder notation. So every set that I write is going to have these squiggly brackets, right? It's going to have these squiggly brackets. Most importantly, what's inside is what I have to kind of look at. So this is a roster method because I'm listing everything out, where this is kind of just a description, okay? And depending on how many numbers we have and what kind of numbers we have, we're going to have some work to do. Now, in some of your questions, you're going to have to be able to go from, I don't want to lose this arc here, go from the so-called set builder notation to the roster method. All right, so you're going to have to read this description and go, okay, what are they? And then from there, list them out. All right, so we got to be able to do that. Okay, so the other thing is, what if there was no numbers in here, right? Between those squiggly brackets, kind of looking like this right here. What do we call those? Well, that is known as the empty set, okay? So also known as the null set, which contains no elements. So it's empty, right? It's kind of like what's in your cart. If you just walk into Walmart with an empty cart, it's an empty cart. There's nothing in it, right? Hopefully there's not anything in it. So an empty set is, you would just see the squiggly bracket with nothing inside of it, okay? But this is also known as, you know what? Let's draw it nicely. A circle with a slash through it. That's also known as an empty set, all right? So now, if you were to just write down 0, well, there is an element in there. The element happens to be 0. So this is not an empty set. Okay? So that's not. you literally have to have nothing in it. So let's do a problem that might be giving an example. Let's say that with set builder notation with a description of what it could be, right? So let's say that P is equal to a set of X for all X such that X is an element of the natural number. Actually, let's not even say that. Let's say that X is less than 4 and X is greater than 10. So, do you know any numbers that are less than 4 but yet also greater than 10? And the answer is no, right? So this right here would give you a result. Let me go ahead and tidy this up a little bit so I have some space to write what I want to write. This will result in a set that has no elements in it. So that would be considered your so-called empty set. So now I gave you some symbols here that kind of threw you off, right? You're like, okay, what's this funny looking E and this N? Well, those are some of the symbols that you need to know, all right? So this funny looking E has an English definition here, as you can see, is an element of, okay? So for example, I can say that 2 is an element of this set. 1, 2, 3, right? So I create a brand new set. It's just 1, 2, 3. So whenever you're given a set, this is the only thing in your brain. That's all you know, okay? So that's all you know. And they're like, okay, is 2 in this set? And you're like, yeah, that 2 is in the set, right? Let me check, right? Same thing in your shopping cart, right? You know, someone comes by and say, hey, do you have any bananas in your cart? And you're like, let me check. Yep, there's bananas in your cart, okay? Now, I can also write that, let me see, 4 is not an element of 1, 2, 3, right? Because it's not an element. Because if you look here, and that's all you know is 1, 2, 3, then 4 is not in there, right? So that is how you see that. Now, I drew this N earlier. This N is actually what the capital N is supposed to look like that I wrote up on top, right? The N right here, right? It's just a capital N. Now, what it usually looks like is something funky like that, right? Now, this is called the natural number. Now, the natural number is also known as a counting number. So this set right here would start at 1, then 2, then 3, just like the way you would count, right? You don't count at 0, you count the first item as 1, right? And it just goes on forever. And that's what that ... means, right? It goes on forever. All right, so those are the natural numbers. All right, so the cardinal numbers, however, the cardinal numbers are basically is asking for how many elements is in your set. Okay, how many distinct. So if it's repeated, it's only written once. All right. So let's say, for example, I give you a set B, and that's going to equal to, I don't know, 7, 9, 11, 13. So because I gave you this set, Those are only 4 numbers you know. You know nothing else, right? Well, how many elements are in here? Well, there's 4 of them. That's right. So you would say n, lowercase n, of b, uppercase b, is equal to 4, right? Let's say I give you c. That's equal to this, right? The empty set. Well, then the n of capital C is going to be 0, right? Because there's nothing in there. All right. So my question is, how many elements will be in the natural number? If it's 1, 2, 3, and it goes on forever and ever and ever, you're going to say, well, that is going to be infinite number of numbers, right? So there is nothing finite about it. It's infinite, right? It goes on to infinity, all right? So what the heck is an equivalent set? Equivalent set says that if they are equivalent if it contains the same number of elements, okay? So let's say, I don't know, where am I on? A, B, C. So let's say that I give you an example here, right? And let's say D is the vowels, right? X such that X is a vowel. Now, you guys know this as A, E, I, O, and U. I know it's sometimes Y, but that's sometimes, right? And let's say that E is equal to X such that X is an element of the natural number and it is between 3 and 7, but including 3 and 7, right? So if you look at that, E is equal to 3, 4, 5, 6, and 7. So how many elements is in D? You'll say 5. How many elements is in E? You'll say 5. So in this case, these two are equivalent. Okie doke. Now, what about equals, right? What about equals? Well, with equal, you're right. You're thinking exactly that. Okay, it contains exactly the same elements, regardless of order or possible repetition. All right, so let's say I got D, E, we're at F. Okay, so let's say set F is equal to 4, 8, 9. And G is equal to 8, 9, 4. Are these two equal? And the answer is yes, because the elements are exactly the same, right? F has a 4, so does G. F has an 8, so does G. F has a 9, so does G. Okay? So, I would just say that set F is equal to set G. All right? So, that, ladies and gentlemen, is everything in these notes. I hope everything is clear. If you have any questions, let me know. See ya. Bye.